So we need to have some very basic language talked about, so our terminology here. So when we're talking about a differential equation, it is an equation of an unknown function. We are trying to find a function that satisfies this equation, and the equation includes derivatives. Now, the derivatives could be higher than the first derivative. It could be the second or third or whatever. So that's what a differential equation is. It's an equation that includes derivatives of some unknown function. That's what this class is all about, is figuring out what that function is that satisfies that equation. An ordinary differential equation is one in which we're only working with one variable. The variable could be t, it could be x, it could be a, it could be whatever, but it's only one variable. The elementary differential equations is applications of the ordinary or potentially partial differential equations, but we're going to be focusing on ordinary in this class. Partial differential equations is when you're looking at a function that has more than one variable. So if you're thinking about the fact that we just finished up Calc 3 and we're now into Calc 4, those are partial derivatives when we're finding derivatives when we have x, y, and z as part of our function. If we wanted to figure out what function satisfied derivatives with those equations with those derivatives, then we'd be in the land of partial differential equations. And that is not what this class is. We are working with only one unknown value in our function. We will talk a little bit about the partial differential equations, but we're not going to spend a great deal on that. That's a different class in its entirety. When we talk about our dependent variable, in this case, in our dependent variable in our differential equation, that is our function. So f of t or y or f of x. So that is dependent is our function. The independent is just like we normally expect the independent to be. In this case, the book that we use uses t as our independent for the most part. Or if we have a function in terms of x, the independent would be x. Most of our functions we're going to be working on in this book is functions in terms of t. So our independent will more often than not be t. What a parameter is a constant value that does not change. We're going to see our constant values could be labeled as r or capital N or omega or mu or h. You'll see a lot of that in this textbook, so we're going to be using that in this course. So those are the ones that are constants. They're not going to change based on the derivative or anything like that. Now, when we talk about a constant, I'm not talking about the constant of integration. That's something else we'll look about, but parameters could be a multiplier on maybe our derivative, or it could be a multiplier as part of our function. The order that when we're looking at is the highest derivative in our equation. When we go through and determine what the order, the independent, dependent, and what parameters are, what we want to look at is either the prime notation or the dp dt notations. So the Leibniz, I think it's what it's called, notation. So when we're looking at this, sometimes it's very clear what the dependent is, and sometimes it's not as clear. Now the book likes to use a function of t, x as a function of t. It's not bad to be able to talk about it as x as a function of t. It just kind of muddies the water initially to begin with. We are so familiar with, by the time we get to this class, that we're so familiar with y as a function of t or f of t or f of x, that when we see these x's with the primes, we don't automatically assume this is what we're talking about as a function. But really, when we see x primes, and in fact, in the homework and or the book, if you've had an opportunity to open the book, you'll see this one wrote as m x double prime. There's no function of t plus b of x prime plus k of x is equal to 2t to the fifth. That's what you're going to see in the book, and that's what you might see in the homework. Now, it's really kind of like, what is going on here? Which one is the parameter? Which one is the independent? Which one is the dependent? So we take a look at this. The way I know which one is the dependent is the one that has the prime notations. So that is the dependent. And by default, whenever I see t, that is going to be as my independent. So in this case, x prime is my dependent. And to make it easier, at least initially, is I make it as a function notation. So it makes it clearer who my independent is. My t is my independent. And of course, if my independent is t, then these other values, b and m and k, must all be parameters. Those are things that are going to be constant. It is not a constant of our integration. It's a constant. It's a thing that's not going to change through the entire equation that I'm looking at. So these are my parameters. These are my constants. And so I have my dependent, I have my parameter. Now I'm trying to determine the order. The order is looking at the highest derivative. Now, the thing that's going to mess you up on this is not having a good, solid foundation of your notations. And I'll help you as I can. The notation here is the primes. So we know that since we see two primes, that means I have to have the second derivative. So this order is 2. This is an order of 2. So that means I have the second derivative as part of the differential equation. Now it's a differential equation because I see I have these two derivatives. That makes it differentiable. It has something was differentiated. And I have the equal sign, and so this tells me I have a differential equation. So this is a differential equation of order 2. My independents are t. My dependent is x of t, or just x. I'm going to stop and I'm going to take a breath. I'm going to make sure I've got everyone that's here today as being noted as here today. Is there any questions so far on where we are?
Okay, so about the parameter. So we start with the m, the b, the k. What other kind of variables could we see in those places?
So as long as it's not a t, right? Any kind of variable that you see, as long as it's not a t and it doesn't have something that's a prime attached to it, then we assume that's a parameter. So it could be omega. So it could be a mu, it could be an r, it could be a huge R, it could be a lowercase r, so cap or lowercase r. It could be anything as long as we know it's a parameter. We know it's going to be a parameter if it doesn't have a prime attached to it. If it has a prime attached to it, then we know that is our dependent variable. And then by default, we usually use t if we're using a function of x in terms of t, would be our dependent, or independent, excuse me.
Okay.
Anything else I can help you with?
Yeah, just making sure. So is x double prime the only dependent variable, or is x double prime, x prime, and x all dependent?
So that's a really good question. So the dependent is actually, this is my dependent. My x of t is my dependent, and the other ones are just primes thereof.
Okay, that makes sense.
What other kind of questions can I help you with on this? All right, so I want you to work on these other 4 or these other 3. So I want you to take a look at A, C, and D, and I want you to pick apart what the order is, what the independent is, what is the dependent, and what are the parameters. I'm going to zoom back in so you can see these right here. So I want you to go ahead, and I'm looking for the order. the independent and dependent variables, and which ones are the parameters? And either you can unmute yourself or you can type it in the chat window for A. What do you think the order is? What do you think the dependent is? What do you think the independent is? And which ones are the parameters?
For A, I think it is, I think it's order 1.
Okay.
I know that the R at the start is part of the parameter, but it looks like a B. I'm not sure if that's the other part of the parameter or not. But,
okay, so the beta, yeah. What else?
For independent, I believe that the P at the start is independent.
Okay.
And the P over K should be a dependent.
Okay. What else?
I think that's it. That's all I've got.
Okay.
So far.
So I agree with some of it. I agree it's definitely an order of 1. And the reason I know it's an order of 1 is because the only place I see a derivative notation is right here. And this is a order of 1 derivative. So it's first derivative. So I agree that it's definitely order 1. Definitely agree with that. Now, if I were to ask you to find, in general, dy dx, who is your independent and dependent if I asked you to find dy dx? And how do you know?
X is independent, y is dependent, because that's how we define a partial.
So that means if I see it in that type of dy dx, this type of notation, I know right out of the gate who is my dependent and who is my independent. Now, the reason I started with this one first is because it made it very clear who was my dependent. My dependent was my function f(x) of t, right? That was my dependent x of t. When it's in this notation, this really is the dependent is going to be p. No matter where you see p, it's a function of t. Now, it doesn't show function notation. It doesn't show it as p of t and p of t and p of t. This is not what it's showing. It's showing it has just p. So similar, if we think about this, and back when we first started to learn calculus, every place there that I had p, I could have replaced with a y. So if I would have rewrote this in something we're more familiar with, if I would have wrote this as dy dx is equal to ry 1 minus y over k minus beta y squared over alpha squared plus p squared, or excuse me, y squared, we could have easily have said, oh, okay, well, y is always our by default. That's how we define it way back in the beginning. If it's a function, then we say that y is our dependent and it's dependent on x. I don't see x anywhere, which is okay. That just means that when I did my derivative, I must have had x as my function of y. So that's all it means, right? So for this, then, it's similar to that, but it's just wrote in different variables, something that we're not as familiar with. So my dependent is going to be my p's. Everywhere I see p, that is going to be my dependent. So it's like saying y, right? We're familiar with y. Whenever we see y is dependent on what x is. This is the same thing, pulling out that information in the way that we're familiar with, but with different variables. So p is our dependent. Now, the thing that kind of messes us up here is that I don't see t anywhere on the right-hand side, but that's okay. T itself is my independent. So if I then go through and mark off everything that is dependent and independent, then whatever's left remaining are my parameters. So my parameters are actually going to be R and K and alpha and beta. So those are all my parameters. So this one has a lot of parameters because there's a lot of variables that are going to be a constant in terms of my equation that I'm looking at here. How was that?
That was really good. I like it.
So let's take a look at C and see if you can digest which ones are your parameters, which ones are your independent, which ones are your dependent. And of course, lastly, what is the order of this? So as you're taking a look, I've got an answer in the chat window. Now, when we're looking at this one's easier than actually A because it's very clear that we are doing the dependent. Your dependent here is going to be y, or you can write it as y of t. Your y is going to be dependent on what t is. So that means your independent happens to be the t. Now that means everything else must be a, if I erase everything else out of there, that means that must be your parameters. So your parameter, as you take a look at this, it's not e, because that's just a function. That means your parameter is your alpha. Now the only thing that may give you a hiccup on this is the fact that I'm taking a derivative of a derivative. So it is an order of 2, and that's because I'm taking a derivative of a derivative. And in fact, what I would have to do here, if I were to find this derivative, is I'd have to use the chain rule. So because it is a multiplication of t times my function, so this is a derivative of a derivative, so the order on this is 2. How are we doing?
It seems like a letter salad, but at a high level, it makes sense.
It is initially a letter salad, and the reason that we have to approach these alphabet soup basically is that when we start solving for these, we need to figure out what it is that we're actually plugging in for and what does it not matter as I start to solve for these. So we need to make sure we pull out the things that are important for solving purposes, and one of them is like, yeah, it's okay. Take a look at this one. Now this is a partial. How do I know this is a partial differential equation and not a ordinary differential equation? How do I know this is a partial differential equation and not just a differential equation? Ordinary or elementary, in fact, differential equation. How do I know what this one is?
There's more than one variable.
How else do I know? Besides the fact that I see u as a function of x and y, how else do I know?
Those Reledes, whatever that Greek letter is.
Yeah, so the deltas on these are not d's, right? So when we see this notation, we know that we're doing the derivatives with respect to. So it's not a full derivative, it's a partial derivative. So it's the derivative of my function u with respect to x, and I'm doing it. And so what is my order on this one? It's an order of 2. I see it here, and I see it here, and I see it here, and I see it here. Now, even if this would have been just, say this didn't have that 2 there, it's still an order of 2 because it is the highest derivative that we are looking at. So we have an order of 2. Do we have any parameters on this one?
I don't think so.
So we don't really have any parameters. We can call a parameter of 1, but really we don't have any parameters. By default, we don't worry about it. If a parameter is 1, we don't worry about it. Who's my independent or independents?
X and Y.
These are my independents right here. Who are my dependents or singular dependent?
U.
So U is my dependent because it is a function of my independence. My independence being X and Y, so that is my dependent. It's my function. What kind of questions do you have for me at the moment?
So the dependent is the function that we're solving for?
Yes.
Okay, all right.
What other kind of questions do you have for me? All right. So now let's talk about seeing whether or not the given function actually satisfies the differential equation. So when we're doing a solution to a differential equation, what we're trying to do is determine whether or not the function satisfies the differential equation. Now, our functions are not equations. We're putting our functions into these differential equations to see whether or not it makes it a true statement. So when we're putting these in, we also have to think about, is there any kind of restrictions? When they're asking us for the largest interval in which this satisfies it, what we want to do is we want to think about any kind of restrictions on either the original function or any kind of restrictions that might show up in the differential equation. Now, as I take a look at this, I know that this looks a heck of a lot like a quadratic, right? We're going to explore these later when they look like quadratics and we're trying to find solutions. Right now, all we're doing is checking it. I'm trying to check to see if I put this function in. Now notice this x prime, this x prime, this x double prime, this x, and this x. These are functions. These are not variables. It looks a lot like a quadratic. And in fact, we'll learn some of the things we use in quadratics to be able to apply to this. But right now, all we're doing is saying, if I take the second derivative of this function, multiply it by 2, add to it the first derivative of this function, multiply it by 6, and then add to that 4 times my original function, do I end up with 0? So the first thing they're asking us for is, what is the interval in which I could actually do this evaluation to determine whether or not this is a solution? So I ask myself, is there any restrictions on this original function? And the answer is no. I can put in any value that I want for an exponential function, e raised to the negative 2t. I can put any value I want in for t. Now remember, we're looking at restrictions for t. So t itself will not have any restrictions, and because the differential equation that I'm looking at is a quadratic, quadratics do not have any restriction. So t can take on any value that is from negative infinity to infinity. Or if you prefer, you can write it as t, which is my independent, such that t is an element of the real numbers. Now this is the interval notation, this is the set builder notation, but this is the largest interval in which I can find equations that satisfy this. They're asking me to check, does this particular equation satisfy this? Is this the only equation? I don't know. But they're asking me to decide whether or not this particular equation, or excuse me, function, this particular function satisfies this equation. Is there any questions so far?
I guess 2 questions. So this is just domain stuff.
Yes. So
okay.
When I look at C, with C, I have a couple of things that are going on. So first of all, I got to ensure that T, whatever T I choose for here, is going to have a positive number or 0. But then the fact that I'm putting in my function in the denominator, I then have to toss out any of my t values that will produce 0. So there are two restrictions, is that the function itself, x of t, cannot equal 0 because it is in the denominator. And then this, we have to ensure that t, whatever t we choose, so the t squared plus 4t plus 1 has to be greater than or equal to 0 because it is in a square root to begin with. Coupling it with the fact that t is in the denominator, then we'll be looking for values of t that make this strictly greater than 0. Does that make sense? So on top of everything else that you're trying to learn here, you also have to go back and think about how we learned domains way back in pre-calculus 1 and 2. On top of everything else, domains are your nemesis or it's your best friend. Depends on if you were good with them or not. How are we doing now? Okay, now let's check whether or not these functions satisfy these differential equations. So I'm trying to determine whether or not I take this function right here and do the second derivative, because this says I'm going to take 2 multiplied by the second derivative, so I better do the second derivative. So x prime of t, which I'm going to need for this part anyways, is going to be, and I'm going to do my regular derivative stuff. So this is going to be negative 2 e to the negative 2t. So derivative of e to the u is e to the u prime. My second derivative is going to be the derivative of that, which is going to be a negative 2 times a negative 2, which gives me now a positive 4 e raised to the negative 2. Now what I'm going to do is I'm going to put in all of these values in here. And so I have 2 multiplied by 4 e to the negative 2t plus 6 multiplied by negative 2 e to the negative 2t plus 4 multiplied by my original function. My original function was e to the negative 2t. And I'm trying to decide, does this thing equal 0 or not? Does it equal 0 or not? Now I can factor out here an e to the negative 2t because it's the same all the way through. So I'm going to factor that out. So I have e raised to the negative 2t. This is going to leave me 2 multiplied by 4 plus 6 multiplied by negative 2 plus 4. And I'm asking myself, does this thing equal 0? Well, what is 2 times 4 minus 12 plus 4? Does that equal 0, yes or no?
Yeah, it's 0.
It equals 0. So the answer is yes. So this does satisfy the solution. So the answer is yes. And what you're going to see is you'll see an equal sign with another line underneath saying that these are equivalent. These are equal. When you see that, it says, yes, we have proved that that is true. How are we doing? Check it in. Doing okay so far? Okay. Try B, please. B and C, please. So we're checking to see, first of all, what is the interval, the largest interval in which we would have this, if it is a function that satisfies this differential equation. What is the largest interval? And also, I want to know what that function does. Does that function satisfy it, yes or no? And I will scroll up so you can see all of that. So go ahead and do B and C, please. Okay, so let's take a look at B. I'm starting to get some answers in the chat window. So the first thing I'm going to do is ask you, this was a test question, perfectly legitimate test question. What is the largest interval in which, provided of course, this function satisfies this differential equation? What is the largest interval that I could have? Now remember, your unknown or your independent is t. What is the largest interval that t can be?
The reals.
Yep. So just like before, t can take on any value in the interval from negative infinity to infinity, or set builder t such that t is an element of the real numbers. So any real number is going to satisfy this. So then we ask ourselves, does this equal this? Does the first derivative equal r times my original function p? Now notice this is not p of t, this is just p. So it's assumed that this is the original function. So the first thing you're going to do is go ahead and do the derivative. So if we have p prime of t, this is going to be c e to the rt multiplied by, here t is the independent, r is a constant, so it's just r. So we can see that this first derivative does indeed equal r of our original function. So yes, this is yes. And sometimes these are so easy, you're like, I think I got this wrong, or I'm not sure how to do this. No, sometimes it really is just this easy. What about on C? What kind of things did you get on C? Let's talk about the domain restriction first. So it doesn't factor nicely. So how do we deal with this when it doesn't factor nicely? Trying to figure out where we're above and below the x-axis.
Is that a quadratic with a sine chart?
Yep. So it's a quadratic with a sine. Yeah, of course it is. But you don't really have to do a sign chart, right? We know that the leading coefficient's positive, so it's up, up. So we just have to figure out whether or not this thing crosses the x-axis, and if it does, where, right? So this is an up, up. We know it's going to have some kind of shape based on the fact that the leading coefficient's positive. It's going to be up, up. So we have to see whether or not this thing crosses the x-axis, and if it does, where, so that we know anything on the left side of the one intercept and the other, anything on the right side of the other intercept is going to be a solution. It's going to be the interval. But it's just a matter of doing the quadratic. So instead of having x, it's going to be t is equal to. So we have negative b, which is -4 plus or minus the square root of b squared, which is 16 minus 4ac, so 4 times 1 times 1, all over 2 times a, which is just 2. So we have -4 plus or minus the square root. Well, 16 minus 4 is going to be what, 12 all over 2? And then of course 12 is the same thing as 4 times 3, so it is √4 times √3. So in other words, it's 2 √3. So this is -4 plus 2 √3 all over 2, which of course just becomes -2 plus or minus √3. So now we found our intersection point. So it does indeed intersect. Discriminant was not 0 or negative. So we know that it is going to intersect. It's going to intersect in 2 unique positions. It's going to be at -2 minus the square root of 3 and -2 plus the square root of 3. Now, because of the fact that this is an up, up, I want the left side and the right side of those zeros. So the t value that I can have is that I can do this as one of 2 ways. So t has to be in this interval between negative infinity and -2 minus the square root of 3 unioned. So this side or this side, which is -2 plus the square root of 3, and then a positive infinity. So I can do it that way with interval notation. My set builder notation is t such that either t is less than, or it has to be strictly less than, so it can't be equal to, strictly less than -2 negative square root of 3, or t has to be greater than -2 plus the square root of 3. We assume that t is a real number, and so that is the largest interval in which that satisfies, if provided, of course, this function satisfies that differential equation. Any questions on that part? Okay, so then we're going to check to see if this differential equation actually works. Let me erase this so I can have this space back. I'm going to come back over here. I'm going to erase this. So we're going to take this derivative. Is my derivative equal to t plus 2 over the original function? So once again, we do our derivative. So we're going to do x prime of t. Now I'm going to rewrite this as t squared plus 4t plus 1 raised to the 1/2. I'm going to use the chain rule. Nice refresher of the chain rule. So it's going to be 1/2, and then it's going to be t squared plus 4t plus 1 raised to the negative 1/2, because I'm using the chain rule, multiplied by 2t plus 4. It's the derivative of the inner function. And so we know that this is going to be 2t plus 4 over 2 the square root of t squared plus 4t plus 1. And that's because it is raised to the negative 1/2, so that brings it back down into the denominator. 2 factors out of the numerator and cancels with a 2 in the denominator, giving me 2 plus t plus 2 over the square root of the t squared plus 4t plus 1, which is equivalent to t plus 2 over x. Is there any questions? Now, could you imagine if I would have said to you in Calculus 1, is this true? Because that's all it really is. Do the damn derivative, right? See if the derivative is equal to t plus 2 over the original function. That's basically what it is. But could you imagine if I would have asked you to do that in Calculus 1? Hey, check this differential equation, see if this is true. You all would have freaked out. But that's basically what it is. Take the derivative. Is it equal to t plus 2 over the original function? The answer is yes. Questions? Comments? Concerns?
Can I see the domain again
Mhm.
on the right? Okay. -2, -square root 3, 2 plus the square root of 3. Okay.
Cool?
Yeah. Thank you.
Yep. Anything else so far? We only have a little bit more and then we're done for today. So what is system? And we're going to get there. Right now we're just checking whether or not these are true. We are going to solve systems of differential equations in this class. We're not there yet. We're just checking, so don't panic. Don't have a moment of, holy crap, I need to know linear algebra. Ideally, you've had linear algebra for this class, but it's okay if you haven't. I will help you out if you haven't, because we're not going to go in depth like we did in linear algebra, but we do need to know a little bit about linear algebra. So on this one, all we're asked to do is show that the given functions form a solution of the system, determine the largest interval again of the independent variable over which the solution is defined, and satisfies the equation. So with this, the first thing I'm going to do is to see what happens when I have x minus y. Well, this is x, and this is y. So I'm going to go ahead and just check x minus y. Okay, so x is e to the t cosine. Actually, I want to do that in blue. Because remember, what I'm checking is whether or not this is a true statement. Are these equivalent? So I'm going to go ahead and do x, which is e to the t cosine 2t minus 1/2 e to the t, the sine of 2t. So that is my x part. I'm going to subtract off my y part, which is e to the t, cosine of 2t, plus 2e to the t, the sine of 2t. So all I'm doing is I'm just doing this x minus y, seeing what I get, where here's x, and here's y. That's all I'm doing. Now when I do this, I see that my e to the t cosine 2t will cancel themselves out, because one's positive and one's negative. Now what ends up happening when I multiply this negative 1 through, because there is really a negative 1 through, that's going to make this a minus 2e to the 2t. So I have minus 2 and a minus 1/2 of e to the t sine 2t. So this is what? 2.5, which is 5/2. So this is going to equal to 5/2 e to the t, the sine of 2t, which is equal to the x minus y. Now what I want to do is I actually want to do the derivative of x. So here's my x. I'm going to come up here and I'm going to do the derivative of x. So x prime, this is a function of t. Now I'm going to do my regular derivative stuff. T is my independent. What's going on between e of t and cosine 2t is a multiplication, so I have to use the product rule. So I'm going to first do, I'll do this here. I'm going to do this part first. This is a multiplication, so I have to use the product rule. This is going to be e to the t, that's derivative of e to the t, is e to the t all day long. The cosine of 2t plus, now I'm going to do the derivative of cosine 2t. So it's going to be e to the t. The cosine of 2t is going to be negative sine 2t multiplied by 2. So that is only the derivative of that first term in the x function. And now I have to do this second derivative. Here's my second derivative, and it's a minus 1/2. So it's going to be a minus 1/2, and I'm just going to put that out front. Again, I have e to the t multiplied by the sine of 2t. So this is, again, the product rule. So I'm going to do the derivative of e to the t. So that's still e to the t. The sine of 2t. Now I'm going to do the derivative of the sine of 2t. So it's going to be plus e to the t. And then the derivative of sine is cosine multiplied by 2. So that is the derivative of x. Now I'm going to clean this up, and you can see that I have this 1/2 here. This negative 1/2 is going to multiply in through. Now this negative 1/2 multiplied by this 2 is going to give me a negative 1. So when I distribute this negative 1/2 onto here, this negative 1/2 and this 2 is going to give me a negative 1. So this is going to end up becoming negative 1 cosine of 2t. That one and that one cancel. That leaves me just, as I did before, e to the 2e, negative 2e to the t, the sine of 2t, minus 1/2 e to the t, the sine of 2t, which we know is negative 5/2 e to the t, the sine of 2t. So what I know by the first system, that x prime, which is all that crap I did up there, is equivalent to x minus y. Now I would have to do the same thing for the other one, checking whether or not the derivative of y is equal to 4 times my x function plus my y function. There it is in all its glory. And that's how you check whether or not they're systems. Mostly it's just refreshing your derivative rules and keeping track of stuff. That's the hardest part about these. Is there any questions on these? Anything at all?